Swayam Prabha. Digital India. Educated India.
Hello everybody. Today it is my third lecture of the module 12. In the earlier lecture I introduced the simplified bending theory of the shell, especially cylindrical shell. So, in this theory we have seen that when the shell is subjected to radial load, then the bending moment is produced at the support. So, bending moment actually propagates as an edge disturbance and membrane solution becomes the particular integral. So, that is the speciality of the simplified bending theory. Membrane theory has to be here used as a particular solution. So, we will show how the membrane theory and bending theory, that is specially the bending theory of this cylindrical shell, can be used in some practical examples to show that the bending moment produced by the radial deformation of the shell is like a edge disturbance. So, it will gradually die out at a larger distance from the edge, but the membrane solution will exist and predominates the behavior of the shell as a particular solution. So, that will be illustrated today by two examples that I have selected for this symmetrical bending of circular cylindrical shell. Okay. Now, let us see a shell element subjected to load that is radial to the surface, normal to the surface. So, I mean that the component of the load along the x axis and along the y axis, that is the tangential direction to the surface, is neglected. So, only load that are important to cause the stresses in the shell are the load normal to the surface, that is in the radial direction, and it is a axisymmetrical type of loading. So, by virtue of that we assume that the membrane shearing forces n x phi equal to n phi x is 0 and n phi is constant along the circumference. So, n phi at any location you will find that n phi is constant along the circumference at any circumferential angle. If n phi is evaluated, you will get the same value. It is dependent only on the x, that is the longitudinal distance from the point of reference. The bending moment m phi, that is in the tangential direction, is constant along the circumference. So, that is another assumption in this theory, that is the shell subjected to axisymmetrical loading and only the loading is in the radial direction. The longitudinal membrane force, that is n x, is taken 0. Hoop force n phi is equal to minus E h w by a, where w is the deformation of the shell, that is the radial deformation of the shell, which causes the change of diameter. A is the radius of the shell. Bending moment along any longitudinal distance measured from the reference point, that is the origin, is given by m x equal to minus d square w by dx square. Now, here d is the flexural rigidity of the shell, and you can find the similarity with the beam bending equation, but in beam bending equation that E I was the flexural rigidity. Here the flexural rigidity will contain this Poisson ratio term also. So, D is nothing but equal to E h cube divided by 12 1 minus mu square. So, with that background we will try to apply this theory to solve two problems of interest. These two problems I will take up one by one. One is your cylindrical pipe subjected to uniform pressure, internal pressure, and it is supported at the end. That means, the boundaries are specified. So, we will see if the length of the pipe is very long, then the how the solution becomes, and when the shell is of finite length, how the solution is obtained. So, after that I will apply this theory to a cylindrical water tank that is very common in our application, cylindrical container containing fluid or retaining fluid or any gaseous substance also. So, because of that the internal pressures are developed and cylindrical wall, the wall is fixed at the base plate. So, there will be some bending moment generated at the junction of the base plate and the cylindrical wall, and that bending moment we will see how it varies along the length of the or along the height of the tank. So, that two problems we will discuss today. We take the deflection of the shell equation, the governing equation for the deflection of the shell. If the thickness of the shell is uniform, then governing differential equation for the bending of shell is given by d into fourth derivative of w with respect to x, that is d to the power 4 w by d x 4 plus E h w by s square equal to z, where z is the radial load, that is load acting in the radial direction normal to the surface. Okay. Now, this equation can be expressed in a form that we can easily find out the roots of the characteristic equation. So, dividing both sides by d, we now obtain d to the power 4 w by d x to the power 4 plus a constant is coming here 4 beta 4 and w is there, and right hand side z is divided by d. So, you can see here z is the load that is acting along the normal to the surface, and it is we call it a radial load, and d is the flexural rigidity of the shell, whereas beta is a characteristic parameter that contains the material properties as well as the shell dimension. The beta to the power 4, that expression is given by E h divided by 4 s square d. A is the radius of the shell and d is the flexural rigidity. Now, substituting d as E h cube divided by 12 1 minus mu square, and simplifying we get beta to the power 4 equal to 3 into 1 minus mu square divided by s square h square. So, once we find the beta to the power 4, beta can be found out, and the unit of beta is the inverse of length, that is, if the length is expressed in meter, then unit of beta will be meter to the power minus 1. Okay. So, with this differential equation, we shall now proceed to apply the solution in some problems that I have mentioned, a shell of finite length supported at the ends and a cylindrical tank. Okay. So, general solution of this equilibrium equation, differential equation have been found, and it can be expressed in two forms. The one form contains the exponential term and the sinusoidal or cosine functions. So, if I see this form number 1, that I can see that w is equal to e to the power beta x c 1 cos beta x plus c 2 sin beta x plus e to the power minus beta x c 3 cos beta x plus c 4 sin beta x plus f x. Why it is another function f x is added? Because f x is added due to the particular solution. The Fx is the particular solution of the differential equation, and you can note that this differential equation is non-homogeneous equation, and therefore, according to theory of linear differential equation, we have to find the solution of homogeneous part, and then it has to be superimposed on the particular solution. Okay. If z is 0, then no particular solution exists. Okay. So, due to the forcing term present in the differential equation of equilibrium, and forcing term is due to this pressure that is acting normal to the shell surface, and it is the solution of that particular integral is f x. Later on we will prove that f x is nothing but the membrane solution of the shell. Okay. Now, here one interesting thing you can note, that e to the power beta x, this term can amplify the deflection or can decrease the deflection if it is associated with minus sign, because beta is always positive, because it contains the material properties and the shell dimensions, which are positive quantity. So, therefore, this term, that is first expression, increase the deflection with the increase of x, but here you can see that e to the power minus beta x, here beta acts as a damping factor. So, in that case this expression actually try to diminish or reduce the deflection of the shell with the increase of distance. So, in a long shell we have seen that if a load is applied at a particular section only, then at a very large distance the effect of the load is negligible. So, therefore, we neglected the constant C 1 and C 2 for a very long shell, but shells of finite length has to be solved containing these 4 constants of integration. The 4 constants of integration can be found by applying the boundary condition at the ends of the shell. So, number 1 equation is useful when the length of the shell is very large, if I drop the constant C 1 and C 2. Okay. Number 2 form, that is W is equal to C 1 sin beta x sin hyperbolic beta x plus C 2 sin beta x cos hyperbolic beta x plus C 3 cos beta x sin hyperbolic beta x plus C 4 cos beta x cos hyperbolic beta x plus f x. These terms that you are noting here, written in terms of trigonometrical and hyperbolic function, can be easily obtained when we substitute e to the power beta x as cos hyperbolic beta x plus sin hyperbolic beta x divided by 2, and also this term e to the power minus beta x, if it is substituted by cos hyperbolic beta x minus sin hyperbolic beta x divided by 2. So, with the use of this exponential term in the form of hyperbolic function, and carrying out term by term multiplication and rearranging the constants, we can write W in this form. This is the second form, which contains the combination of trigonometrical and hyperbolic functions. Okay. Here again f x is the particular integral due to the load acting on the shell. This form 2 is useful when the shell is of finite length. Okay. Now, let us apply this theory or solutions that we have written here in the earlier slide for a shell of finite length and subjected to uniform pressure with supported ends. So, here I consider a shell of length L. It is a closed shell and it is subjected to uniform internal pressure. The thickness of the shell is h and the length of the shell is L. So, for convenience we take the center of the shell as the origin. Okay. There is a point of reference from which we measure the distance x. The cross section of the shell is shown here and it is subjected to internal pressure that is acting radially. Okay. Now, if the origin is taken at the center of the pipe or shell here that you are noting in this figure, then we can take advantage of the symmetrical terms in the expression of deflection. So, since the shell is symmetrical with respect to the center of the shell in respect of loading, geometrical parameters and support, then we can only assume that the deflection of the shell shall contain only the even functions. So, let us identify what are the even functions in this expression. Okay. Even function in this expression, you can see that all the terms are product of two functions, one is trigonometrical function and another is hyperbolic function. Now, let us examine the first function sin beta x sin hyperbolic beta x, that is the product. Sin beta x is a antisymmetrical function, sin hyperbolic beta x is also antisymmetrical function. So, product of two antisymmetrical function is a symmetric function. Similarly, here you can see cos beta x is a symmetrical function and cos hyperbolic beta x is also symmetrical function. So, product of two symmetrical function is again symmetrical function. But if you examine these two terms, sin beta x is a antisymmetrical function, whereas cos hyperbolic beta x is symmetrical function. So, product of these two is antisymmetrical function. Similarly, this cos beta x is a symmetrical function and sin hyperbolic beta x is antisymmetrical function. So, we shall drop this constant C 2 and C 3, that means, we need not consider this term containing the coefficient C 2 C 3, because our problem is symmetrical and we take only the even function in the expression of deflection. Okay. So, with that advantage, we can now reduce the deflection equation with two constants of integration. So, what are the two constants of integration? C 1 and C 4 that were associated with the sine function and sine hyperbolic function and cos function and cos hyperbolic function. So, both are now symmetrical function associated with a particular integral. Okay. Internal pressure is assumed positive inward. So, it is acting outward because the pressure, that is internal pressure, fluid pressure or whatever may be, it is acting outward. So, therefore, it is taken with a negative sign. So, Z is taken as minus P. Now, since the forcing term is a constant term, Z is a constant here. So, we expect that particular solution is also constant. So, according to theory of undetermined coefficients in the linear differential equation, we now assume that particular integral is W p is a constant C. So, substituting C in this expression, because C is a constant. So, when it is differentiated, you will get 0 here, but here you will get 4 beta to the power 4 into C, and beta 4 is nothing but E h divided by 4 s square d. So, W p, that is the particular solution, is nothing but C, now comes out as minus P divided by 4 beta to the power 4 into d, where d is the flexural rigidity. Substituting the value of beta 4 and d, we now simplify W p as minus P s square divided by E h. So, general solution of this differential equation of the bending of the cylindrical pipe now reduces to W is equal to C 1 sin beta x sin hyperbolic beta x plus C 4 cos beta x cos hyperbolic beta x minus P s square divided by E h. Okay. This term, the last term, is due to the load in the radial direction, that is the internal pressure P. Okay. Now, here you are seeing that two constants of integrations are appearing in the solution. So, that have to be found out considering the condition at the ends. Since the shell is of finite length and the boundaries are defined in the problem, we can now apply the boundary condition. In this problem, we assume that shell is simply supported at the ends. So, boundary conditions now becomes at x is equal to plus L by 2 or minus L by 2. Say if x is measured positive towards the right from the origin, then right hand support of the shell is denoted by located at x is equal to plus L by 2, whereas left hand support of the shell is located by the distance or coordinate, that is x equal to L by 2, okay. And W is 0. Minus L by 2 locates the support at the left hand and plus L by 2 locates the support at the right hand. Okay. W is 0 as well as bending moment is 0, because it is simply supported condition. So, applying the above conditions in the following equations. Following equation is this, containing two terms of two constants of integration, that is C 1 and C 4. Now, the solution will contain the combination of trigonometrical function as well as hyperbolic function. So, sin beta x, sin hyperbolic beta x and cos beta x, cos hyperbolic beta x. So, first substitute the condition, that deflection condition at x is equal to L by 2. So, substituting this condition and x is equal to L by 2, now we get C 1 into sin alpha into sin h alpha plus C 4 cos alpha cos h alpha minus p square by E h. So, this is from this equation, that directly we substituted x is equal to L by 2 and we assume this parameter alpha as beta L by 2. So, you can see here, when I substitute x is equal to L by 2, this term becomes C 1 sin beta L by 2 and into sin hyperbolic beta L by 2 plus C 4 cos beta L by 2 into cos hyperbolic beta L by 2 minus p square by E h. So, this is the result of this substitution of x is equal to L by 2 and assuming alpha equal to beta L by 2. Okay. So, first equation we got from the first boundary condition, that W is equal to 0. Second boundary condition is obtained when we consider the bending moment at the support plus L by 2 or at minus L by 2 is 0. So, considering this condition, that is we have to now obtain the second derivative of this equation, and after substituting x is equal to L by 2, again we got C 1 cos alpha cos hyperbolic alpha minus C 4 sin alpha sin hyperbolic alpha equal to 0. Because of differentiation, this particular integral term, that is a constant here, will disappear. So, therefore, you are getting the term containing C 1 and C 4. Okay. This equation can be solved because it contains two unknown quantities C 1 and C 4, other quantities are known. So, we can solve two simultaneous equation with two unknowns. Okay. So, here I used this solution with Cramer's rule. So, we write the equation in matrix form. This equation is written in matrix form. So, if I write this equation in matrix form, then coefficient matrix becomes sin alpha sin h alpha cos h alpha, then cos alpha cos h alpha minus sin alpha sin h alpha into the vector C 1 and C 4 equal to p square by E h and then 0. Okay. C 1 and C 4 are the unknown constants of integration that have to be evaluated by solving this matrix equation. Okay. So, using Cramer's rule, we now define this parameter delta, that is the determinant formed using the coefficient of this matrix, that is I call the coefficient matrix. So, sin alpha sin hyperbolic alpha cos hyperbolic alpha cos hyperbolic alpha minus sin alpha sin hyperbolic alpha. So, that is the determinant using the coefficients of the matrix 2 by 2 matrix. Then delta 1 I define as determinant p square divided by E h cos alpha cos hyperbolic alpha 0 minus sin alpha sin hyperbolic alpha, and if I expand this determinant, you can see this expansion and expansion of determinant will lead to this equation minus p a square divided by E h sin alpha sin hyperbolic alpha. Delta 2 we now write it in this way, sin alpha sin hyperbolic alpha cos alpha cos hyperbolic alpha p a square by E h 0 determinant, and we expand this determinant, we now get it p a square by E h cos alpha cos h alpha with a minus sign. Okay. So, delta 1 and delta 2 are obtained. We can now have to find this determinant delta. So, determinant delta is found, and after substituting this C 1 as delta 1 by delta, we now obtain C 1 as p a square by E h multiplied by sin alpha sin h alpha divided by sin square alpha sin h square alpha plus cos square alpha cos h square alpha. Similarly, we get C 4 as delta 2 by delta equal to p a square divided by E h into cos alpha cos h alpha divided by sin square alpha sin h square alpha cos square alpha cos h square alpha. Okay. So, the numerator term is that you are seeing is directly coming from this expansion of determinant with delta 1 and delta 2, whereas denominator will contain the expanded form of the determinant delta. Okay. So, the denominator that you are seeing here sin square alpha sin hyperbolic square alpha plus cos square alpha cos hyperbolic square alpha is nothing but expansion of the determinant formed by the coefficient of the matrix equation, okay, 2 by 2 matrix. Okay. Following identities are used to simplify further the constant of integration. So, what are the identities? One identity is trigonometrical identity, that is 2 sin square alpha equal to 1 minus cos 2 alpha, and another is 2 cos square alpha equal to 1 plus cos 2 alpha. Then other two are this hyperbolic function identity, that is 2 sin hyperbolic alpha equal to cos hyperbolic 2 alpha minus 1, and second one is 2 cos hyperbolic alpha equal to cos hyperbolic 2 alpha plus 1. So, using these identities here we can now express the C 1 and C 4 in simplified form. So, C 1 contains p a square by E h 2 sin alpha sin h alpha divided by cos 2 alpha cos hyperbolic 2 alpha. Similarly, C 4 contains p a square divided by E h 2 cos alpha cos hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha. So, we can now write the complete solution. So, complete solution is C 1 sin beta x sin hyperbolic beta x plus C 4 cos beta x cos hyperbolic beta x minus p a square by E h. C 1 and C 4 are now completely known. So, therefore, substituting C 1 as this quantity and C 4 as this quantity in this expression, we can now get the equation in this form, W is equal to minus p a square divided by E h into 1 minus 2 sin alpha sin hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha into sin beta x sin hyperbolic beta x, that means this term. Then the other term is 2 cos alpha cos hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha into cos beta x cos hyperbolic beta x. So, you now get the complete equation of the deflection. Okay. So, it is written again here, and substituting this E h by a square as 4 d beta to the power 4 and using this beta as 2 alpha divided by L, we can find beta as 2 alpha divided by L. we can now express E h by a square, that is appearing in this equation as 64 alpha to the power 4 into d divided by L to the power 4. Okay. So, using this parameter, we now express the deflection as W is equal to minus P L to the power 4 divided by 64 L to the power 4 into d. D is the flexural rigidity of the shell, multiplied by 1 minus 2 sin alpha sin hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha sin beta x sin hyperbolic beta x minus 2 cos alpha cos hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha cos beta x cos hyperbolic beta x. Okay. So, since this shell is supported symmetrically and loading is also symmetrical and the shell thickness is also symmetrical, then means it has uniform flexural rigidity. So, the maximum deflection we obtain at the center of the shell. So, at the center of the shell, substituting x is equal to 0 in the final expression of the deflection, you can see this term will be vanished, because when you put x is equal to 0 here, this will be 0 and as well as this will be 0, and cos beta x when it is evaluated with x is equal to 0, it will be 1, cos hyperbolic beta x also will be 1. So, the maximum deflection is obtained as W is equal to minus P L to the power 4 divided by 64 alpha to the power 4 into d bracket 1 minus 2 cos alpha cos h 2 alpha divided by cos 2 alpha plus cos h 2 alpha. That means, second term is a hyperbolic function. So, cos hyperbolic 2 alpha. Now, some important conclusion we will draw from this expression. Let us consider the shell is very long. So, in the long shell that we use this alpha is equal to beta L by 2. We used alpha equal to beta L by 2. So, naturally alpha parameter will be very large for very long shell. So, now if you see, if you substitute here cos alpha which is very high value, then this term becomes very large value, denominator will be very large. So, naturally this fraction will be negligible. So, hence maximum deflection for a very long shell is obtained as P L to the power 4 divided by 64 alpha to the power 4 into d, because this term can be ignored for the reason that the cos hyperbolic 2 alpha will be very large because of this large lengths L alpha is equal to beta L by 2. So, second term inside the parenthesis approaches 0 and therefore, we write the expression of deflection for the long shell at the center with this expression W is equal to minus P L to the power 4 divided by 4 beta to the power 4 L to the power 4, and in place of d we now substituted E h cube divided by 12 1 minus mu square. Okay. And also in place of alpha we brought this parameter alpha is assumed as beta L by 2. So, beta is appearing here. Now, substituting beta to the power 4 as we have obtained earlier as 3 into 1 minus mu square divided by s square h square, and then L to the power 4 is already there, and we substituted this d here, also we substituted written here, then d is also written here E h cube by 12 1 minus mu square. So, after simplifying this expression you will find that W is equal to minus P s square by E h. Now, this expression can be examined. Say P a by h is nothing but hoop stress in a cylindrical shell subjected to internal pressure. So, stress divided by strain, that is it divided by modulus of elasticity, that is E, will give you the strain. So, stress by E, that is sigma by E will give you strain, and strain multiplied by radius will give you the change in radius. So, that is the radial deformation. So, you can see that W that we get here for very long shell is nothing but your membrane solution P s square by E h. So, for very long shell we now conclude that W is equal to minus P s square by E h, and two interesting things we can note here. If the shell is very long and it is a thin shell, cylindrical shell, of course, we are dealing with the cylindrical shell, behaves as if ends are free and deformation is due to hoop strain. So, that is obvious for a very long shell, the effect of bending moment can be neglected. The effect of end supports upon the mid span deflection is also negligible. So, if the particular integral does not appear in the shell deflection equation, then the effect of this support, that is there is no question of this applying the boundary condition, because the shells are very long and the boundary condition will not affect the deflection at the mid span. So, that two conclusion we can arrive from this expression. Expression for bending moment can be obtained by differentiating the deflection equation 2 times with respect to x. So, differentiating twice the expression with respect to x, of course, you have to multiply the differentiated quantity with the flexural rigidity of the shell. It is also multiplied with d, and finally, we get the bending moment expression as m x equal to minus p l square by 4 alpha square into sin alpha sin hyperbolic alpha divided by cos 2 alpha cos hyperbolic 2 alpha cos beta x cos hyperbolic beta x minus cos alpha cos hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha into sin beta x sin hyperbolic beta x. So, this is the expression for bending moment of the shell. Okay. Maximum bending moment occurs at the center again because of symmetrical problem, and maximum bending moment we get from the earlier expression, when is substitute x is equal to 0. So, if I substitute x is equal to 0, this term will not be coming into picture, and this term cos beta x cos hyperbolic beta x will be 1. So, therefore, maximum bending moment will get minus p l square divided by 4 l alpha square into sin alpha sin hyperbolic alpha divided by cos 2 alpha plus cos hyperbolic 2 alpha. So, one interesting thing you can see that again if alpha is large, that is for very long shell, this quantity approaches 0 or becomes very small quantity. So, therefore, very long shell, the bending moment at the center is negligibly small. So, that it is observed very clearly from this expression if cos 2 hyperbolic 2 alpha is large. Therefore, the middle portion of the shell is under the action of merely hoop stresses, and in the middle portion of the shell and its vicinity the membrane state of stress exists. So, that is an important conclusion for very long shell. Okay. Now, let us apply this solution to another problem that I have told in the beginning of this lecture, that a cylindrical shell has to be analyzed, and that type of shell is frequently used as water retaining structure or storage tanks in many applications, and for the solution we take the wall thickness as uniform, but it is not necessary that wall thickness should be uniform, it may also vary. So, in that case differential equation for the deflection of the shell will contain the coefficient which is variable in x. Radius of the shell is a and it is built in at the bottom edge. So, the shell is fixed at the bottom edge. The depth of the water in the tank is d. Water or any fluid whose density is taken as gamma. Now, assuming that cylindrical tank is infinitely long shell we will use this condition that shell is infinitely long, but it is not necessary also. If the condition at the two ends are defined and the shell is treated as a tank of finite length, then also the equation or solution can be obtained. So, our intention is to find the hoop tension and bending moment in the shell. Okay. So, we proceed with that differential equation d to the power 4 into w divided by dx to the power 4 plus 4 beta to the power 4 into w equal to z by d, where z is the internal pressure in the tank, and at a distance x, x is measured from this base is taken as the reference plane. So, if I take this as the origin and x is measured upward positive. So, at a distance x, the depth of the water causing the pressure is d minus x. So, d minus x into gamma will be the pressure at this level, and the variation of the pressure you can see it is linear hydrostatic pressure. The governing differential equation of this shell now can be written as d to the power 4 w divided by dx to the power 4 plus 4 beta to the power 4 w equal to minus gamma d minus x by d. Instead of z, we can substitute this quantity. Solution of that equation is given earlier, and it is written here again. W is equal to e to the power beta x into C 1 cos beta x plus C 2 sin beta x plus e to the power minus beta x into C 3 cos beta x plus C 4 sin beta x plus f x. F x is the particular solution due to internal pressure. Okay. Because the shell is very long, so as we have treated earlier that these two terms have to be dropped, otherwise the deflection and bending moment at the other end will be unbounded, because this quantity e to the power beta x will increase with x, because beta is a positive quantity. So, therefore, we have to retain only these two constants of integration C 3 and C 4, and the solution now written as w is equal to e to the power minus beta x C 3 cos beta x plus C 4 sin beta x plus f x. So, this is the final solution, and two constants of integration now have to be determined from the end condition. Okay. So, homogeneous solution we have obtained, and particular solution now we can obtain using this the theory that earlier I have explained, because the particular integral is due to the forcing function, which is a linear function, and therefore, we assume W p as c into d minus x. So, we assume W p as c into d minus x, and substituting this W p in the differential equation, we finally get the particular solution as W p equal to minus gamma into d minus x s square divided by E h. So, this is the particular solution. Simplification of course, is made by using this quantity beta to the power 4 as E h divided by 4 s square d. So, now complete solution is written as W is equal to e to the power minus beta x into C 3 cos beta x plus C 4 sin beta x minus gamma d minus x s square divided by E h. So, this is the particular solution, and again we will prove that particular solution is also the membrane solution. So, let us prove this. So, at any level, say x, that is defined, x is measured from the bottom of the tank, the hoop stress is given by gamma into d minus x into A divided by h. So, hoop strain is gamma into d minus x into A divided by E h. Also, we can write hoop strain as the change in circumference divided by the original circumference for a small element of the shell, which subtends an angle d phi at the center. So, length of the part of the circumference of the shell, which subtends an angle d phi at the center, is a d phi, and this length is changed due to radial deformation. So, changed length of this element is a minus w into d phi along the circumference, and original length was a d phi. So, if I take the ratio of this to a minus w into d phi minus a d phi divided by a d phi, this will yield the hoop strain. So, hoop strain is now obtained as gamma into d minus x into a divided by E h. Now, from this quantity, if I want to solve w, so this is the expression which connects w with the hoop strain. So, if I solve this equation for w, then what we get? We get w is equal to minus gamma d minus x a square divided by E h. You can see from this equation d phi will get cancelled. So, therefore, this circumferential strain will be nothing but minus w by a. So, minus w by a is nothing but gamma into d minus x into a divided by E h. So, w can be readily found as minus gamma into d minus x a square divided by E h. So, it is again proved that particular solution and membrane solution are same. The complementary solutions actually depends on the boundary conditions, and it may be looked as a disturbance emanating from the edges. So, but this disturbance dies out gradually because we have taken a damping like factor e to the power minus beta x. Okay. At x is equal to 0, w is equal to 0, dw by dx is equal to 0. So, this is our given boundary condition, and applying this boundary condition in the deflection equation that we obtained here, if I apply the boundary condition w is equal to 0, dw by dx is equal to 0 at x is equal to 0, we obtain now two constants C 3 as gamma a square d divided by E h and C 4 equal to gamma a square divided by E h into d minus 1 by beta. So, after substituting C 3 and C 4, we can now write w as w is equal to minus gamma a square d divided by E h into 1 minus x by d minus e to the power minus beta x cos beta x plus 1 minus 1 by beta d into sin beta x. So, this is the complete expression of the deflection, where all the parameters are known, because d is the depth of the fluid or depth of the tank. If the fluid is up to the full height of the tank, then d will be height of the tank. H is the thickness of the shell, a is the radius of the cylindrical shell, and other quantities you know that beta is the characteristic parameters that we have found earlier. So, once you know w, then the membrane stresses, only one membrane stress is of importance, that is n phi, others are insignificant in the problem and these are neglected. So, n phi equal to minus E h w divided by a, and substituting w here we get n phi as gamma a d into 1 minus x by d minus theta beta x minus 1 minus 1 by beta d. So, this is one constant parameter multiplied by another function xi beta x. Now, theta xi are the functions which contains this exponential term with cosine terms or the sine term. So, these functions are defined as, there are several functions which contain this combination of exponential term and cosine and sine term. So, here you can see I have written 4 functions, phi beta x equal to e to the power minus beta x cos beta x plus sine beta x, xi beta x equal to e to the power minus beta x into cos beta x minus sine beta x, etc. So, here we have used only these 2 functions theta beta x and xi beta x. Okay. So, it is written in the functional form, and the maximum deflection will be obtained somewhere, but this deflection you have to calculate by plotting the graph, or you can impose the condition where the slope is 0 to get the maximum deflection. the membrane force n phi can be obtained as minus E h w by A, which is nothing but gamma a d into 1 minus x by d minus theta beta x minus 1 minus 1 by beta d, this is the parameter, into xi beta x. Bending moment is obtained by calculating the second derivative of this deflection function and then multiplying the second derivative with the flexural rigidity. So, bending moment is obtained as minus gamma s square capital D into small d. You should distinguish between two symbols. Capital D is the flexural rigidity of the shell, whereas small d is the depth of the tank or depth of the water in the tank, divided by E h into minus theta double prime. Theta double prime indicates that second derivative of this quantity, second derivative of this quantity, because second derivative of these two terms will be 0, then we are getting minus 1 by beta d, second derivative of that quantity xi beta x. Okay. So, m x is written after simplification, that is putting the value of this various parameters that appearing here, d as a flexural rigidity, that E h cube by 12 1 minus mu square, and bringing them in terms of beta, that is the characteristic parameter of the shell. We now write the bending moment in the shell as 2 beta square into gamma a square capital D into small d divided by E h into minus xi beta x plus 1 minus 1 by beta d theta beta x. Substituting the value of beta and d, again it can be expressed in another form. So, m x is equal to gamma a h d. A is the radius of the shell, h is the thickness of the shell, d is the depth of water or height of the tank, divided by root over 12 1 minus mu square into minus xi beta x, this is the function, plus 1 minus 1 by beta d into theta beta x. So, m x can be calculated now along the height of the tank, and maximum bending moment you can see is only at the fixed end. So, fixed end provide restraints. So, maximum bending moment is calculated at x is equal to 0. So, maximum value is obtained by putting x is equal to 0 here, and we can obtain that maximum value is nothing but gamma a d h divided by root over 12 into 1 minus mu square into 1 minus 1 by beta d. Okay. Now, such type of tanks are very common in our construction industry, whether you use it for steel tank or this reinforced concrete tank. The provisions of various codes for design have been available. So, here is such one provision that is given by the code IS Indian Standard 3370 part 4. So, in this code the bending moment, hoop tension and base shear coefficients for different values of a combined geometrical parameter are given. Now, tables in the codes provide coefficients for bending moment, hoop tension, base shear at different heights of the cylindrical shell. Base shear of course at the base, and other quantity you can obtain at different height. Okay. The coefficients are available up to certain combined ratio of height of the tank, diameter of the tank and thickness of the tank wall. So, this is the actually limitation of this code. So, you will get this coefficient up to a parameter that I have defined as, I call it as alpha. Alpha is h square, that is height square divided by diameter into thickness. So, if this parameter is greater than 16, no coefficients are available in the code. However, using the general theory, the coefficients are generated for different values of alpha also, and then once the coefficients are known from the code, the moment is given by coefficient into gamma h cube. h is the depth of water and it is with a cubic quantity. So, h cube. Ring tension, that is the hoop tension developed, is nothing but coefficient into gamma d h. Okay. Let us discuss a numerical problem. A circular cylindrical water tank has a diameter 18 meter, total depth of the water 8.7 meter, thickness of the cylindrical wall 350 millimeter, density of the water 10 kilonewton per meter cube. We have to calculate the maximum value of the bending moment, hoop tension and shearing force, of course, you can calculate, produced by hydrostatic pressure. Okay. Now, let us see this tank. The diameter of the tank is 18 meter, the height of the water here is 8.7 meter, density of the water is 10 kilonewton per meter and thickness of the wall is 0.35 meter. So, with this given data, I use the expression for maximum bending moment m max equal to 1 minus 1 by beta d into gamma a d h divided by root over 12 1 minus mu square. After substituting the numerical value, we can obtain, first let us calculate the beta. So, beta to the power 4 is calculated as 3 into 1 minus mu square divided by s square h square, and after substituting the numerical value, Poisson ratio for concrete, it is RCC tank. So, we have taken as 0.15. Substituting the value of this parameter, beta comes out as 0.5214 meter to the power minus 1. So, now maximum bending moment will be at the base, and here we take d is equal to h in the formulation. So, substituting all the parameters in this maximum bending moment expression, here we now obtain the maximum bending moment as 124.75 kilonewton meter per meter. So, this is the result of maximum bending moment. Meridional stress, hoop stress, that can be calculated n phi equal to minus E h w by A, and the expression after substituting w and written using the special function theta and xi, we can now express n phi as gamma a d into 1 minus x by d minus theta into beta x minus 1 minus 1 by beta d into xi beta x, and after substituting the numerical value here, we now and expressing all the quantities, that is the force unit in kilonewton and length unit in meter, we now get n phi as 1566 into 1 minus x by 8.7 minus theta beta x minus 0.7796, the function xi beta x, and its unit is kilonewton per meter. So, the variation of n phi is obtained for different values of x along the height of the tank, and that variation is plotted here, and you can see the maximum hoop force is obtained here, say at a distance of this around 5.7, and variation of hoop force is maximum at this point. So, let us summarize today's lecture. In this lecture, we have discussed the solution of the differential equation for the radial deformation of the cylindrical shell subjected to symmetrical loading. The application of the theory has been illustrated with an example of cylindrical pipe of finite length subjected to internal pressure. The theory of bending of cylindrical shell has been further applied for the solution of a analysis of a cylindrical tank containing fluid. Lastly, I have given a numerical example to illustrate the theory. Thank you very much.